Welcome to this online training about the high bandwidth memory found in certain Altera FPGAs. My name is Steve. This training is available for desktop viewing, as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the link provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you about that later. In this training, you will learn about high bandwidth memory, or HBM, a next-generation high-speed memory technology built directly into Altera Agilex 7 M series, Altera Stratix 10 MX, and select Altera Stratix 10 DX devices using System-in-Package, or SIP, technologies. You'll see why this integration offers a very compelling solution for many of today's most demanding applications. You'll learn about the features of the hardened HBM controller found in these devices and how to parameterize and integrate the HBM IP into an Altera Quartus Prime project. Finally, you'll learn about HBM controller efficiency and how to optimize and measure the efficiency of your own HBM interface design. As you proceed through the training, it is recommended that you have basic familiarity with memory technologies such as DDR memory and the Arm AMBA 4 AXI or AXI4 interface standard. AXI4 is the primary interface standard used for accessing the HBM from the FPGA core, so understanding the signaling used will make it much easier to implement a design. See the AXI4 specification from Arm, linked here, to learn the details of this interface. Here is the agenda for this training. In the first part of the training, you were introduced to the HBM standard, including a look at its unique features and its architectural design. In this second part, you'll learn about the features of the hardened HBM controller, or HBMC, and the user interface required from your design to communicate with the controller. In the final part, you'll see how to implement the interface in the Altera Quartus Prime software, and how to measure and optimize the performance and efficiency of the interface. Note that when HBM is mentioned in this training, it is referring to both the HBM2 and HBM2E standards unless otherwise noted. Also note that the architecture and implementation of the HBM2 found in Altera Stratix 10 MX devices and Altera Stratix 10 DX devices is similar, unless otherwise noted. References to Altera Stratix 10 MX devices will also refer to Altera Stratix 10 DX devices. Now let's focus on the features of the hardened HBM controller. Here is a listing of the features of the HBMC that will be covered. Some of these features may be familiar to you if you have previously used external memory interface IP. First, it's important to understand HBMC bursting options, since bursting is one of the keys to memory access performance. The HBMC supports two bursting modes, BL4 and pseudo BL8. A BL4 burst is a standard burst of 4 transactions, where the starting address is automatically incremented for each transaction. The pseudo BL8 mode is simply 2 BL4 bursts back to back. However, only a single starting address is used, so 8 transactions occur based off the starting address. A BL4 burst transfers 32 bytes, while a BL8 burst transfers 64 bytes. As you'll see later, the supported burst transaction mode is selected when the IP is parameterized and is also specified through the AXI4 interface size signal of the write and read address channels. The HBMC supports command scheduling and command priority options. For command scheduling, the controller schedules incoming memory access commands to achieve maximum efficiency at the DRAM interface using multiple AXI4 transaction IDs. The controller follows the AXI4 interface ordering model defined in the interface's specification. The controller also supports options for setting the priority of a command. Command priority control is available with the standard AXI4 interface, as well as when the optional Avalon interface is used with Altera Stratix 10 MX devices. When AXI4 is used, command priority can be set for both read and write commands using the QoS signal in the read and write address channels. One of two priority levels can be selected, either normal or high. Commands with the same priority level are serviced by a round-robin scheme. If the Avalon interface is used for accessing the HBM2 in an Altera Stratix 10 MX device, an option can be enabled that adds an additional sideband signal that, when active, indicates that the current read or write command is a high priority command and should be serviced before others. The HBMC also supports a fixed starvation limit for read commands. Due to the command scheduling just described, commands can be reordered to minimize the turnaround time for switching between writing and reading. Because of this, read commands could be delayed for a long period of time. However, the controller honors a fixed starvation limit, so read commands don't have to wait for all reordered write commands to complete. A read command is issued if the starvation limit is reached. The starvation limit is not adjustable. Besides command scheduling, the HBMC in Altera Stratix 10 MX devices also supports data reordering for read data. The need for data reordering comes into play if different transaction IDs are used. As mentioned, the AXI4 interface includes a transaction ID signal to allow for multiple threads of data transfer. If all transactions use the same ID, the data must arrive at its destination in order, so no reordering by the controller is required. However, if different transaction IDs are used and data reordering is disabled, command rescheduling is free to reorganize the read requests for optimal memory access. Without data reordering, it is up to the user to organize and use the incoming read data correctly based off the transaction ID. If data reordering is enabled, a reorder buffer is used to maintain the order of read data so it matches the order of read commands issued to the controller. This makes it easy to manage the incoming data without having to check the transaction ID, but it can increase the latency for read data if it must stay in the buffer and wait for other data to arrive first. When accessing the HBM2 or HBM2E stack, the user logic provides a 28 through 31-bit size read or write address to the HBMC, depending on the device, the size of the memory, and extra options enabled. The address is made up of the row address, the column address, a bank address, extra subordinate ID bits if the 4x4 switch is used in Altera Stratix 10 MX devices, a stack ID bit for 8 high stacks, and extra bits that must be set to 0. The choice of a BL4 or pseudo BL8 burst is made using the least significant column address bits. The HBMC supports different address ordering schemes that you can select and use based on memory access patterns. Different address ordering may provide better controller efficiency. The chosen addressing scheme determines how the address bits are ordered in the AXI4 interface read and write address channels. The HBMC automatically handles the remapping of the logical address of the command to a physical memory address in the DRAM stack. The available address ordering options are listed here. An example of the addressing options is shown here. Based on the previous slide, for an Altera Agilex 7 M-series device with an 8-high stack using pseudo BL8 accesses, the address bus is 30 bits wide and organized in one of the 3 orders mentioned. For detailed diagrams of the address formatting for all devices and available options, see the HBM2 or HBM2E IP user guide. By default, the controller automatically manages and performs memory refresh. The the frequency of refreshes is automatically adjusted based on the current operating temperature of the memory stack. The stack constantly provides this temperature information to the controller through a dedicated temp signal. However, for Altera Stratix 10 MX devices, you can choose to have manual control over memory refreshes. Manual refreshing is not available and not required in Altera Agilex 7 M series devices due to the improved controller-managed refresh available in those devices. With the manual refresh option, you can choose to refresh the entire stack or refresh on a per-bank basis. The HBM2 stack can also be put in a self-refresh mode. Manual refresh commands are issued using the separate Arm AMBA APB interface from the user logic to the HBMC. See the user guide for details on the format and timing of commands for user-controlled refresh. Along with different refresh options, different pre-charge options are available. Pre-charging must be performed after a memory access to close that bank and allow the activation of another bank. Auto pre-charging is an option to have the controller issue the pre-charge command automatically at the completion of a memory access without explicitly requesting a pre-charge. The timing of when to pre-charge based on the way memory is accessed can improve efficiency. By default, the HBMC handles the issuing of pre-charge commands to the memory stack based on a subsequent read or write transaction address being in the same bank or a different bank. However, you can also manually indicate that an auto pre-charge command should be issued along with a read or write command. User-controlled auto pre-charging is managed through the AXI4 interface using the AR user or AW user sideband signals. If using the Avalon memory mapped interface option in an Altera Stratix 10 MX device, an optionally enabled additional sideband signal is issued along with the read or write command to mark it for auto pre-charge after command execution. The additional signal works in a similar way to the additional signal discussed earlier used for command prioritization. You can select one of two policies for how the auto pre-charge will be issued, hint or forced. Hint is the default. With the hint policy, the request for pre-charge is used as a hint to the controller of what to pre-charge, but the controller decides when to actually issue the pre-charge command based on the addresses of subsequent transactions. With the forced policy, when a pre-charge is requested, the command is immediately issued after the current read or write. Note that the policy to use can be different for reads and writes if desired. Next are the thermal management control mechanisms. These were discussed in the first part of the training, but here's a refresher. Recall that it's the controller that is responsible for making temperature-based adjustments to the operation of the memory stack. The HBMC honors the refresh rate specified by the temp signal from the memory stack discussed earlier. The controller will adjust to the refresh rate specified by this signal, which is set for the hottest die in the stack. The temp signal can get set to a lower refresh rate if the stack is running too hot. The HBMC also monitors the cat trip signal. If the catastrophic temperature sensor trips, the controller immediately stops all traffic and stalls indefinitely. The device must be powered off and allowed to cool before the sensor is reset. The HBMC can also perform thermal throttling. Thermal throttling is a feature of the controller that can help control thermal runaway if the dies in the memory stack heat up too much. This is done by disabling the AXI4 ready signals for a period of time, delaying the handshaking required before a signal is executed. Throttling can help prevent a catastrophic event. Throttling is based off a user-specified junction temperature and throttle ratio. In Altera Stratix 10 MX devices, you can specify the threshold temperature and the throttling ratio. In Altera Agilex 7 M series devices, a specific temperature cannot be set, but separate throttling ratios can be set for two temperature ranges, 85 to 94 degrees Celsius and for greater than 95 degrees. Finally, if the power down feature is enabled, the HBMC can put the memory stack into a power down mode if it has not been accessed for a long period of time. Each of the 8 channels in the stack can be powered down individually. The power down status of a particular channel is available via the APB or Axi4 Lite sideband interface, depending on the device. Now let's take a look at how to connect your user logic to the HBMC. As mentioned, the standard user interface to the HBMC for all devices follows the Arm AMBA 4 AXI interface specification. Each port serves one pseudo-channel's read and write operations. Each controller for the 8 channels has 2 Axi4 interface ports, since each channel consists of 2 pseudo-channels. Each port consists of the 5 channels that make up the Axi4 interface standard, not to be confused with channel access to the HBM. These channels are read address, write response, write data, and read data. As such, each channel controller is made up of 10 Axi4 interface channels. Individual signals are named using the prefixes shown for each channel. Individual port signal names in the device are referenced using a formatting scheme that depends on the device. For Altera Stratix 10 MX FPGAs, the format is AXI XY port name, where X corresponds to the HBM2 channel number and Y corresponds to the pseudo-channel number. For example, AXI01AWID refers to the write address transaction ID signal of the port corresponding to HBM2 channel 0 pseudo channel 1. For Altera Agilex 7 M series FPGAs, the format is channel X UY port name, where X and Y again refer to the channel number and the pseudo channel number respectively. Additional user sideband signals that get enabled with certain options for Altera Stratix 10 MX devices are prefixed with AXI extra. All 5 transaction channels of the Axi4 standard use the same valid ready handshaking protocol to transfer address, data, and control information. This two-way flow control mechanism means both the source and destination of a transaction can control the rate at which the information moves between them. The source generates the valid signal to indicate when the address, data, or control information is available. The source interface for each channel is listed. The destination generates the ready signal to indicate that it can accept the information. The destination interface for each channel is also indicated. A transfer between the source and destination only occurs when both the valid and ready signals are high. The signaling for the address write and address read channels is shown here. A few things are important to note about signal use with the HBMC. The address signal width will depend on the factors mentioned earlier, including the size of the memory stack, the device used, and other enabled options. The length signal is used in an Axi4 interface to indicate the number of transfers in a burst. The HBMC supports a single burst transfer of length 4 or 8 as discussed earlier, but the encoding of the length for these single transactions is different between the different device families. Plus, to support bursts of more than 2 for Altera Stratix 10 MX devices, an option must be enabled in the parameters for the IP, which will be discussed later. For details on the encoding, see the IP user guide. The size signal is normally used to select the size of a transfer in a burst, but the HBMC only supports 32-byte transfers, so this signal is ignored by the controller. However, user logic must set this to a fixed value of 101 binary. The burst signal, which normally sets the type of burst, is ignored by the controller for anything other than incremental bursts. As such, this signal must be set to 01 binary for normal operation. Finally, the user sideband signal indicates a manual request for an auto precharge command after the current read or write transaction, as discussed earlier. For the write data channel, most of the signals are used for their standard roles. If ECC is enabled by setting the data bus width to 288 bits, the WUser sideband signal is used for the additional 32 bits of ECC data. For Altera Stratix 10 MX devices only, the WUser signal is divided into user data and a 4-bit user strobe signal. The strobe signals indicate which byte lanes of the 32-bit ECC data are valid. In the write response channel, the controller should always respond with OK. Exclusive accesses are not supported, so the controller will only respond with OK or an error. Finally, in the read data channel for Altera Stratix 10 MX devices, the R user signal is split into user data for ECC and user error DBE to indicate double bit errors. The response options are the same as in the write response channel. Besides the main AXI4 interfaces to each pseudo-channel, there are some additional or different interfaces that may be used depending on the device and option selected. For Altera Stratix 10 MX devices, an Arm AMBA APB sideband interface is used along with the main AXI4 interfaces for control and debug operations that do not require the bandwidth of AXI4. This includes things like the user-controlled refresh, temperature monitoring, and accessing ECC status registers. APB signal names are prefixed with UR. Also for Altera Stratix 10 MX devices, if the option to use Avalon interfaces instead of AXI4 is enabled, all pseudo-channel connections use standard Avalon signaling. Signals in the interface will use the name formatting shown here, with X representing the channel number and Y representing the pseudo-channel number. Additional signals for command priority control, auto precharge control, and ECC error detection are included if they are enabled. Finally, for Altera Agilex 7 M series devices, an AXI4 Lite sideband interface is used instead of APB. This performs many of the same functions as the APB interface. Signals in this interface are prefixed with SB. As always, see the user guide for details on the use of these additional or alternate interfaces. This concludes part 2 of the training. If you missed part 1 or you'd like to continue on to part 3, you can register for free at the links shown here. To learn about additional resources available to help you with using high bandwidth memory, continue to the next slide. For more information about HBM2 and HBM2E in Altera Stratix 10 MX and Altera Agilex 7 M series devices, see the online resources listed here. The HBM IP user guides go into detail on the architecture of the memory in these devices, as well as all aspects of implementation, including IP parameterization, IP signaling, clocking, and simulation. The design example user guides walk through the entire implementation flow, including design simulation, and how to use the design example for performance testing. If you will be using the HBM2E DRAM found in Altera Agilex 7 M series FPGAs, the NOC documentation and associated training go through all the details of how to include the NOC in a design, which is required for an HBM2E implementation. Finally, the Arm AMBA 4 AXI specification describes in detail the standard interface required for accessing the HBM found in these devices. Altera offers many options for learning about our FPGA products and for training on their use. The Altera FPGA YouTube channel contains a number of 5-minute quick videos along with longer, more in-depth training. The Altera FPGA training website is the place to go to learn about our recommended curriculum for every type of user and to register for a class. While there, you can register for over 300 e-learning courses made up of narrated slides presented in an interactive player, some of which include labs and demos. You can also register for one of our full-day instructor-led training classes taught by experienced training engineers, either in person at a local office or virtually over the web. All instructor-led courses have hands-on lab exercises to practice the concepts you learn. If you need further assistance, Altera FPGA provides many self-help resources. Check out the landing pages, accessed from the main Altera website, that are dedicated to specific FPGA technologies like high-speed interfaces and external memory. Finally, you can also view and post questions to the community forum, monitored by skilled Altera FPGA application engineers. One more thing. You will receive a link to a short survey where you can provide feedback. We'd greatly appreciate it if you'd fill out that survey. We're constantly updating and improving our training materials, and your feedback helps us create the materials that you want. Thank you for your feedback. My name is Steve, and I want to thank you for taking this training on the high bandwidth memory found in Altera FPGAs.